example. Oh, it is. I see.
All right, so find the first derivative of this by implicit differentiation. And the direction of by implicit differentiation is really just telling us don't try to solve it for y in terms of x first before taking the derivative. You know, if you came across a problem on a test or on the AP where it said just find the derivative, you do it any way you want. It's just in this particular case, the skill is implicit differentiation. That being said, it's not the easiest thing in the world to get this in terms of x, so solve for y in terms of x. I'll show you what it looks like in a few minutes. It's interesting. Page 60. All right, so we have a product rule for this part and a product rule for this part because we're looking at the product of two functions, y as a particular function, also x as a particular function. So part A, first is x squared times the derivative of the second, so dy dx, plus the second function, y, times the derivative of the first, which would just be 2x. So that addresses the first product. Then we're going to add to that the derivative of y squared x. So first function, y squared, times the derivative of the second, which would be dx dx. All right, so first is y squared times the derivative of the second function would be dx dx. I'll write it, but you wouldn't actually have to write it because that's going to cancel to a 1. Dx divided by dx is equal to 1. Plus the second function, x, times the derivative of the first, which would be 2y. All right, so plus the second times the derivative of the first, 2y dy dx. Oh, that is a highlighter. Undo. And the right-hand side has a derivative of 0 again because of the constant. Because when you're following the chain rule, you're taking the derivative of the y squared as something to the second power, becoming 2 times that something to the first power, times the derivative of whatever the something is. Right? Just as a general kind of working definition, just so you don't have to think about the theory every single time you do a problem, what we do is every time we take the derivative of a y term, we just slap on a dy dx.
Okay. I wasn't here on Thursday, and I thought that I caught myself up on Friday. Did I miss something else? Like, I don't know what this implicit differentiation is.
I was out on Friday, too. So.
No, I was out on Thursday.
Oh. All right.
Oh, you missed like 1.5.
You missed the lesson.
Yeah, that's
You missed the lesson.
the lesson on Thursday. Yeah. Let me. Okay. So
It was like 70.
now the housekeeping is not going to be as meaningful because it's like we're going to rewrite it just to combine, through multiplication a couple of terms. It's not going to seem like we're accomplishing much, but we will be, believe it or not. Alright, so not as nice as my false start, because the false start thing is beautiful. This one, we have 2 dy dx's. Alright, well, that's okay, we can handle that. What we're going to do is take anything that doesn't have a dy dx and shoot that over to the other side. So negative y squared minus 2xy you have a common dy dx, so factor that out. And then divide by the multiplier of dy dx, so divide by x squared plus 2xy. All right, so we're going to get dy dx equal to negative y squared minus 2xy over x squared plus 2xy. And so that's our derivative, and it's not pretty, but it is a derivative. It represents the rate of change, instantaneous rate of change of this equation. I don't even know if it's a function. I mean, we'll look at that in a minute. For particular values of x and y. Right? Now it says find the first derivative when x is equal to 2. Not quite as nice as some of the other problems where you could just go into y4 in your calculator, for example, and go that route. Here, I need to actually plug in an x and a y value. So I'm going to go back to my original function. Actually, let me do that above it. Plug in a 2 for x, just to get the corresponding value of y. So 2 squared y plus y squared times 2 equals negative 2. All right, so everything's divisible by 2. I could divide out that. Make it 2y plus y squared equals negative 1. It's quadratic. So we're looking at y squared plus 2y plus 1. All right, that's a perfect square trinomial, y plus 1 squared. All right, so we get y equals negative 1 when you solve that. So we know that the x value is 2. The y value that goes along with that x value in the original equation, seemingly a function, possibly, would be negative 1. So if I want my derivative at the x value of 2, I'm looking for the derivative at the coordinate 2, negative 1. All right, so that's where I'm working, and I'll just pop that in for my dy dx. So dy dx at 2, negative 1. So let's see, negative 1 plus 4, 60, no, 4 minus, so 0? Oh, that's fun. So undefined, all right, so that could mean a couple of things. It could mean that we're dealing with a derivative that doesn't exist, but it could also mean that we're in the realm of like cusp versus vertical tangent kind of thing going on here. Right? So if that's the case, then what I would need is the limit.
Mr. Karen,
Yeah,
that was awesome.
Yeah, sure. I would need the limit of the function as we're approaching 2 from a particular direction. The only issue here is, though, and this is kind of beyond the purview of the course, this is a function in 3 dimensions. So it's not something that we could actually easily find the limit of, because if we're looking for the limit of this surface, really, it's way more complicated than it may seem. So moral of the story is we're just going to leave our answer at undefined. We're not even going to make a claim in terms of tangency or anything like that. But let me just show you what the graph would look like really quickly. 3D graphing. Get rid of that. What is it? X squared y plus y squared x? Is this going to be on the test? No, no, it's not. It's not going to be on the test. But we like learning. I looked at it, I acknowledged that it was there, and I lost it. Did it say y squared x?
Yes.
Okay, thank you. All right, so you look at something like this and you say, well, of course I have to do it with implicit differentiation. And again, whether or not you're a pro at that is a different story. It's just recognizing that it's an implicitly defined function. It tells you that, well, if it's implicitly defined, then I would use implicit differentiation. Why? Because I don't have y all by itself. Now, if I could get y all by itself, then I could take the derivative using another technique. So how would I go about getting y all by itself? I'd have to solve for y. How would I solve for y? Well, there's ways. So I have a y squared term that has a coefficient, I'm going to write it as x. Then I have a y term that has a coefficient of x squared. And I'm going to bring over that 2, so plus 2 equals 0. All right. Now, you can, I mean, it's quadratic. It's just we're treating the x as a coefficient of y. But the strategies by which you would solve a quadratic are still in play. You like completing the square, use completing the square. If you like quadratic formula, use that. Completing the square can be a little messy. Quadratic formula is messy, but it's the simplified form of completing the square. So, you know, by definition, it should be a little bit less messy. All right. So this would be my A term, my B term, and my C term. So y would be negative b minus the square root of my b squared, so x squared squared, minus 4 times my a term times my c term, all over 2a. All right, so all over 2x. So negative x squared, I don't know why I just did the minus. It's plus or minus. If you're doing a calculation, you do it one at a time. That's Monday morning. So x to the 4th minus 8x all over 2x is what y would be equal to. All right. You can clean it up a little bit. I mean, you may not define this as clean, but it would be easier to take the derivative in this form. So we'd be looking at, if I split my fraction, this over this, which would be negative 1/2 x, and then the plus or minus, and then the other part is pretty much as is. So x to the 4th minus 8x under the radical with a 2x on the bottom.
What happened to the squared and the negative x squared?
Oh, I actually divided it by the 2x.
Oh, so you just subtracted
So
it.
I just subtract the exponents. All right. So then when I go to take the derivative, it should be somewhat doable. Let me do it over here. And let me thin out my utensil. Oh, that's not it. That's this one. And get rid of that. So dy dx would be equal to negative 1/2. That's the part that becomes easy because of the simplification. But then the other part, plus or minus, the other part would involve quotient rule, all right? Unless you want to bring the bottom up and make it a little product chain rule action. I don't think it really makes a difference either way. All right, so denominator squared, low d high. So my high would be 1/2 x to the 4th minus 8x to the negative 1/2 times 4x cubed minus 8. So that's the low d high minus the high d low is going to be minus 2 times the radical. And I mean, I suppose there's some more housekeeping that could be done at this point. I mean, we have some radicals that can be rationalized and things like that, but I don't know that it's necessarily useful to do that because once I have my derivative, I can then do my substitution somewhere. Yeah. And the place that it makes the most sense to do the substitution, just to get right to the final answer without having to go too crazy, would be in the red here, because you'll have a term that has a radical x to the 4th minus 8x on the bottom of a fraction. Plugging a 2 to that, you're going to get 16 minus 16. So you're going to get 0 in the bottom of a fraction for just this part of it, and it'll never not be in the bottom of a fraction. So that would be your license to call this undefined. You know, so instead of actually doing the rote calculations, you just kind of reason it out. And we'd say dy dx when x is equal to 2 specifically would be undefined. All right. But we, I think, did less work when we did it implicitly. You know, all this work was just get it into a form that we could use to find the derivative. After we did that, taking the derivative wasn't too bad. But just getting it into the appropriate form took all the work. So,
So, Paul's back, I'm not sure you already said this, but the second way, is it implicit or is it not?
explicit.
Okay.
Yeah, once you get it solved for y in terms of only x, it's an explicit.
Okay.
All right. Number 3, part A, sketch the graph of the hyperbola. All right, so you just need a rough estimate really of it. So if you have a general sense of what a hyperbola looks like, then this graph is already pretty much completed. All right, center's at 0, 0. You have a horizontal movement of radical 6 units, which is somewhere between 2 and 3. So plot a point, you know, just ballpark it. All right, a vertical change somewhere between 2 and 3, because this is the square root of the denominator of the y term. So the square root of 8 is somewhere between 2 and 3, closer to 3. All right, so same idea, just a little bit closer to 3. All right. We'll ask them to a rectangle. Draw your diagonals. Plus. Alright, so that's the framework for our hyperbola. Now, would this hyperbola open upwards and downwards, so like that, or is it going to open to the side?
Side to side.
Side to side. Alright.
It's an X minus Y.
Yeah, if the x term is positive, then it's going to open outwards. If the x term is negative, it's going to open upwards and downwards. Alright. If they're both positive or both negative, then it's not a hyperbola, it's an ellipse. Okay, so that's generally what it looks like. It's not a function. Okay, so if you were to solve this for y in terms of x, it would be fine. You'd get an answer. You'd get something that you could create a graph out of. But you'd have a plus or minus in it because of the square involved with the y. All right. So now part B is asking for the equation of a tangent line at the point 3, -2. So you could just kind of roughly estimate where 3, -2 is just to get a sense. It's like somewhere in this neighborhood. So we're looking for a tangent line kind of like this. All right, so I need my derivative. First, I'm going to rewrite it as 1/6 x squared minus 1/8 y squared equals 1. Make it a little bit nicer to work with, more power rule-y. Derivative of the x term, we do that the way we normally would, which would be 1/3 x. All right. Now for the y one, it becomes 1/4 y times dy dx equals derivative of a constant goes to 0. All right. Now we need to find the slope of the tangent line. So we have a coordinate 3, -2. We can plug that in right away, or we could solve for dy dx in terms of x and y and then plug it in. I think it's going to make our lives a little bit easier if we plug it in right away. Because it's going to be easier to move the numbers around than it is to move the letters around and then replace them with numbers. Okay, so 3 goes there, -2 goes there. All right, so 1 plus 1/2 dy dx equals 0. So I'm going to subtract the 1 and then multiply by a 2. So dy dx would be equal to -2 at that particular location. Now it's saying find the equation of the tangent line. All right, so I'm going to use my point slope form. Y equals m times x minus x sub 1 plus y sub 1, and replace the x sub 1s with the x sub 1, y sub 1 with the coordinate, and the slope, the m, gets replaced with the -2. And so that would be the equation of a tangent line, of the tangent line, with these characteristics. All right, and then you kind of play it out a little bit. If you distribute the -2 to the -3, you get 6 minus 2 is 4. I mean, it was a crappy drawing, but it is conceivable that if you drew a nice tangent line, a reasonable estimate, that it could have a y-intercept of 4. We knew going in that it would have a negative slope, so that's pretty consistent. So it's feeling like a pretty good solution.